In this recording, we're going to investigate the connections between Euclidean domains and principal ideal domains. And our goal is to prove the following remarkable fact. Every Euclidean domain is a principal ideal domain. Now, I ask you to review the proof of the fact that the set of integers is a principal ideal domain before you watched this video. If you have not done that, I would really encourage you to review that proof because this is a direct generalization of that proof. We are going to let D be a Euclidean domain, and we are going to assume that its Euclidean valuation function is named U. And our goal is to show that if I is an ideal inside D, then I is equal to the ideal generated by A for some A living inside my domain D. Now I'm going to split my proof up into two cases, and the first case is very trivial. If I is equal to the zero domain, then I already know that I is the domain generated by zero, and hence is a principal ideal. So my second case is going to be that I is not the zero ideal. So I contains some non-zero elements. Now I'm going to define a set S, and the set S is going to be defined to be all of the valuations of elements that are living inside I that are not zero. So the set S is made up of all of the nu of x's where x is in I and x is not zero. Now since I is not the zero domain, S is not empty. And it's also clear because of how an evaluation is, a Euclidean evaluation is defined, that this is a subset of the natural numbers unioned with zero. In other words, the set of non-negative integers. And I'm going to make two observations about S. If zero actually lives inside S, then zero is the smallest element inside S. And if zero does not belong to S, then it turns out that S is a non-empty subset of the natural numbers. And hence, the well-ordering principle, let me make that writing just a little bit clearer. The well-ordering principle implies that S contains a smallest element. So regardless of whether or not zero is inside S or not, we have a smallest element. We're going to let little s be the smallest element of capital S. And let me make my capital S's all have these little serifs on them to make it easier to distinguish my capital S's from my little s's. So now little s is going to be the smallest element of set S. There's one more thing that I want to say about this S. Since little s, let's make my notation just clearer. Since little s lives inside the set S, there exists some element A inside I with nu of A equal to little s, because that's how you get inside set capital S. We also know something else. If x is any element of I and x is not 0, then I know that the nu of x has to be at least as big as nu of A, which is the smallest element inside set S, and set S contains all of the nu of x's. And that's a pretty important fact, so I want to kind of box this in and say this is important. Remember this. Now what I'm going to do is do a double inclusion proof. My claim is going to be that the ideal generated by I is actually all of A. And we're going to do a double inclusion proof. The easy direction is to show that the ideal generated by A is a subset of I. If X lives inside the ideal generated by A, then I know that X is equal to R times A for some R inside my domain D. But A is also inside I, and I is an ideal, so that implies that X is inside I, since I is an ideal and A belongs to I. So that tells me that the ideal generated by A does indeed belong to I. Well, now let's look at the inclusion going the other way. We now need to show that the ideal I is contained inside the principal ideal generated by A. I'm going to let Y be any element of set I. And what I know is that because D is a Euclidean domain, and I want to be very precise here, and I know that A is not equal to 0, there exist Q and R inside D such that Y is equal to Q times A plus R, and I know that nu of R is strictly less than nu of A, or R must be equal to 0. And this is the definition of a Euclidean valuation function. And that boxed in part is going to be important to remember. Well, now what I want to do is I want to look at this. I can take this equation and I can solve it for R, and I get R is equal to Y minus QA. And Y is inside the ideal I, and A is inside the ideal I, so that makes this difference inside the ideal I because I is an ideal. And now what I want to do is I want to kind of think about what that says. So what we have now is that R has two properties. First of all, R is inside the ideal I. Second of all, I know that R is either equal to 0 or nu of R must be less than nu of A. But I also want to remember that being inside of I says you are either equal to 0 or your valuation, nu of R, would have to be bigger than or equal to nu of A. And if you think about what these two things together are saying, they're saying that the only thing that R can be is 0. So these two things together say R must be 0. And I want to kind of make that clearer. If R was not 0, then we have nu of R is less than nu of A by property 2, and we have nu of R is bigger than or equal to nu of A by property 1, and that is a contradiction. Hence, we can conclude that R is indeed equal to 0. And that says that y is actually equal to q times a plus 0. In other words, y is equal to q times a, which means y is indeed inside the principal ideal generated by A. And so what that says is that ideal I is a subset of the ideal generated by A, and with the first inclusion, that lets us conclude that I is equal to the principal ideal generated by A. And since I was an arbitrary ideal, we can conclude that all ideals of D are indeed principal ideals. And hence, D is a principal ideal domain, and that completes the proof.